And I'm live. Okay. Yeah, she's recording. Happy days. Right. Haven't done a solo one in ages. Haven't done a conversation in even longer. It's on my to-do list. There's been a lot of, I suppose, self-inflicted anxiety over, oh, but I should do this and I should be doing that and I haven't done this and I haven't done that. And there's been a cloud of that in my head for the last kind of 2 months. But look, I have a 5 month old of a business to run, and life, no different than anybody else, kind of gets in the way. But I was thinking about it too much, I think. Like if I spent 1/10 the time I did ruminating over not doing it on doing it, I'd have 20 conversations and 100 hours of solos done. Off the cuff maths mightn't be great there or realistic, but anyway, I digress. Here I am, done beats perfect. I said I'd fucking take a little bit of my own advice and just basically sit down and just doing it. No notes, no nothing, a vague idea of what I want to talk about, and we'll see where this goes. So come along on the journey with me if that doesn't sound too up my own arse. Anyway, I didn't know what to talk about, but I wanted to start from the start for some reason. So I was like, where will I start from? And I was like, just take the lazy way out and start from the start, the actual start. So let's go all the way to the start. The Big Bang. Actually, I don't know if it did go because I don't know if there was sound at the time of the Big Bang. There was certainly no one to hear it. So maybe we'll just glaze over that a little bit at the minute. So where did the Big Bang start, and what was the Big Bang? Just to give you an idea, the Big Bang is the starting point as we know it, or as we have theorized it, as we think it was, where the universe came from. What's the universe? The universe is everything. Absolutely everything. If you're thinking of something outside of the universe, that means that it could only be in another universe. Wait, there's more than one universe? There could well be. There's a theory called the multiverse. The idea being that when our universe went and exploded into existence out of nothing, if that is what has happened, then why wouldn't that happen again and again and again and again? So the multiverse theory is basically that even now, somewhere, either in a different dimension or in maybe an alternate universe or an alternate space in time, is constantly happening. So universes are constantly exploding into existence. But look, we only have the one universe to observe, so we'll just stick to our universe, namely the only universe, which is basically everything. So everything that you can think of, from the furthest galaxies and stars and black holes and planets, and everything that ever has been or ever will be, is in what's called our universe. And as best we can figure out, it all started with this thing called the Big Bang. Now, oh yeah, actually, this is what I wanted to talk about more so than the Big Bang. Now, I was going to do the whole Big Bang and the whole universe thing, definitely. But what I want to talk about is, this is the kind of the sentiment. The sentiment is this idea of high resolution what? High resolution understanding is the wrong word. High resolution interpretation, conceptualization is a better one. So we have understandings of certain things. So I personally have what I would consider a very high resolution understanding of how to grow pea shoots, because that's what I do professionally. My business grows pea shoots and other microgreens and sells them, and I do it better than anybody else in the country by quite a margin. And it's grown from strength to strength over the years and has kind of blown up on me in this year, say. But anyway, I understand the process, from sourcing the raw ingredients to the processes that put them together, to growing the actual stuff, to harvesting it, to packing it, marketing it, selling it, distributing it. Every step of the way, I know in minute detail the nuances that make what I do a success. So I have a very high resolution understanding of my own business. I need to. You can't be successful in anything really unless you have what I would consider a high resolution interpretation of something or conceptualization of something. Now, my resolution of the Big Bang and how the universe came into existence, I suppose, is kind of relatively... And the word's gone. Relatively what? I've just said it about 10 times. High resolution. There we go. My understanding of everything that's happened from the Big Bang till now is relatively high resolution. It's not nearly as high resolution as I would like it to be. But I kind of have an idea of a lot of things that got us from to me sitting down and recording this podcast. And the reason that I have that high resolution, or relatively high resolution understanding, is because I personally am a wide achiever and not a high achiever. So I'll glaze over not every, but most of the most significant events from the Big Bang till now with low resolution. So I'll be able to talk about, the red shift, which I'll mention now in a minute. I'll be able to talk about the universal speed limit of light, of gravity and electromagnetism, and little bits and pieces along the way, to planetary formation, stellar formation, to the evolution of life and different things. I can speak for, a couple of minutes on each one of those things, but not in depth about any of them. So I have a kind of a broad, high resolution understanding of everything from the Big Bang till now, or at least I'd like to think I do. And one of the main motivations for me recording this podcast was to start talking, to see what I know, in order to shine light on what I don't know. So no doubt I'm going to get to a stage whereby I'll be explaining something and then I'll have to stop myself and go, oh wait, I actually don't know what I'm talking about here, or I'm after contradicting something that I'm after just saying. So maybe revisit this, maybe have a look at this, maybe I have too low a resolution understanding of this particular piece and I might just make a note of it or whatever. Or maybe somebody listening will be able to either correct me or fill in a couple of blanks. So imoffthelead@gmail.com will always get me. So if I say something that's incorrect, or if I've been too nonchalant at how I glaze over a particular part of the process, or maybe I completely ignore a particular part of the process from the Big Bang till now, let me know. We're all here to learn. So yeah, so you can have high and low resolution interpretations and conceptualizations and understanding of things. So my microgreens business, I have a high resolution understanding of that. I mentioned, I think in the last podcast, that I wouldn't have phrased it like this, but I would have a very low resolution understanding of gayness, say. So my understanding of what it means to be gay is that you are physically and psychologically attracted to the same sex. And I'm pretty much kind of running out of my understanding of what it means to kind of be a gay person alive in the world today. It's something that I don't really understand. And when you can only kind of rhyme off something by its definition and know absolutely none of the nuances, what it's like growing up as a gay boy in an all-boys school, like that must be fucking, more difficult than being a straight guy. But, I don't understand it. And likewise for women, and likewise for bisexual people, and all sorts of different sexualities. The area of sexuality, even fucking heterosexual sexuality, I don't fucking understand that. I don't understand my own sexuality, let alone others that are the same as me, let alone others who are, kind of different than me. So I would have a low resolution understanding of that, a very low resolution understanding of that. And I suppose that the sentiment of this podcast is to get across that idea that people can have low and high resolution understandings of different things. So when you're maybe disagreeing with somebody, or let's say, I'm sure you can think of somebody who has an alternate opinion to something than you do. Let's say you disagree with somebody on a particular subject, or maybe all subjects, but you have a disagreement. Ask yourself, who is the higher resolution conceptualization of their position? Who can articulate their position the best? And can they articulate it the best because they're just articulate and they have a great command of the English language, or because they actually know a lot more details about the subject than you do? Because if you disagree with somebody, and in the same breath you know that the person that you are disagreeing with understands the subject material far better than you, maybe shut the fuck up. Maybe think to yourself for a second am I disagreeing? Am I in disagreement with this person because they're wrong, or because I'm ignorant to the facts? So I suppose that's the overarching reason I'm recording this. It's to get across this idea that some people have higher resolution conceptualizations and understandings of on certain subjects than others. Now, that's obviously not to say that somebody who has a higher resolution understanding of something can't be wrong. Of course they can. Like, I've heard extraordinarily articulate people reason why, you know, black people are inferior to white people, for example. So just because somebody is very knowledgeable and very articulate in a certain subject, and you're possibly not as knowledgeable or as articulate, that doesn't necessarily mean that that person is right and you're wrong, not by any stretch of the imagination. There might be just a bias, say, and there often is, and that's another thing that we have to do as individuals, is examine our own thoughts and try and find where our own biases lie, because we all have them in fucking spades. We really do. And that's bad enough that we're biased, but what's worse is that we be biased and be completely oblivious to these biases, whatever the word is. Anyway, the universe exploded into nothing. Sorry, the universe exploded into something from nothing. Where? Everywhere. When? I can be a bit more specific there. It's about 14 billion years ago. Is it 13.8 or... Yeah, I'm going to stick my neck out and go 13.8 billion years ago. Look, there about 14 billion years ago. Universe has exploded from nothing. Now, that idea that the universe exploded into something from nothing is pretty low resolution, you might agree. Now, if I was to increase my understanding of that, I'd read a book written by a guy called Lawrence Krauss called A Universe from Nothing. And this, if you're interested, is, as far as I'm aware, I haven't read it. I've actually gone to see him speak on it. He's a really interesting guy, and I was kind of I enjoyed the talk, but I was none the wiser come the end of it. So he wrote this book, but it's for a general audience. It's not a scientific paper. It's not convoluted or verbose. It's kind of to the point, and it's his effort to explain it as a physicist to people who aren't physicists, basically. So I have a very low resolution understanding of what the actual Big Bang was, other than, again, by definition, you know, the universe exploded from nothing. Anyway, it happened everywhere because all of space and time, everything was condensed. It's almost as if if you visualize or conceptualize the universe as a giant bubble, a giant spherical bubble, if that giant spherical bubble just got smaller and 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 smaller until it was a dot, and then it went smaller and smaller and smaller and smaller and smaller and smaller. So if you reverse the Big Bang basically from now, what we think happened was it exploded and expanded and continues to expand now. And that's where this whole idea of the red shift. Ooh, I'm going to guess an astronomer's name here. I'm not, because it won't come to mind. But there was a famous astronomer who discovered what I think is called the red shift. So when he was examining the furthest stars from where we are, from our viewpoint, the Earth. So when he aimed his telescope to the furthest reaches, to the darkest points of space, and went further and further, essentially back in time, because if you imagine a grenade going off, bits are blown in all directions. The bits that are furthest away from where the grenade went off, it obviously took them longer to get from where the grenade went off to where they are now than to the bits that kind of blew up and went into the ground beside it. So the amount of time it took for that piece of grenade fragment to travel from where it exploded to where it is now, the furthest part, say, that's equivalent to the 14 billion years that the universe as we know existed. Now, if you were sitting on Earth looking at these furthest pieces, there's a red tinge of anything at the outer reaches of the universe. And that's to do with how light bounces back off these images. Because when you look at something through a telescope, what's actually hitting your pupils and what you're actually seeing and processing is light that bounced off that object and came back and kind of hit you in your retina. But as I said, everything that we examine at these further ends of the universe tends to look as though you're looking at it through a red filter. There's this kind of red tinge to it. And his name really came to me there. It's on the tip of my tongue. Or it's not on the tip of my tongue, but it's in there. It'll come. This famous astronomer, was it Hubble? Did they name this telescope Hubble after this guy? I should really know that. But anyway, again, this is the beauty of kind of just sitting down and talking. It sheds a light in your own ignorance. Things that you thought you knew. Like if somebody was to ask me, do you know who discovered the redshifts? I would say, yeah. And then you go, who? And you go, oh, and I do know, it's in there somewhere. But it's locked away. It might come to mind. Something like Hurst or something is in my head, but I don't know why. Was it Hubble? I can actually see a picture of the guy sitting down in this big planetarium-sized telescope thing with a pipe. Could have been Hubble. I'm not sure. Anyway, the reason that there's this red kind of glow off these things is because the objects are still moving away. That was his big discovery. The furthest objects from Earth, say the things that are on the outermost limit of our universe, are traveling away from us. And interestingly, they're traveling away from us faster than the speed of light. But you might say to yourself, but Fran, nothing can move faster than the speed of light. And you'd be right, because we've probably all heard that idea that nothing can move faster than the speed of light, but that's right in two ways. A, it means nothing can move faster than the speed of light. It's grand, universal speed limit. Nothing can move faster than the speed of light. We all get that. But also, in a more nuanced way, nothing can move faster than the speed of light. So nothing, actual empty space, so the expansion of the universe, that can move faster than light. So when you hear somebody say nothing can move faster than light, they're kind of right on two counts. One, that no physical thing can move faster than the speed of light, but also that nothingness itself can actually move faster than the speed of light. So when something's moving away from you, whatever way light hits something that's moving away and bounces back to us, again, I have a very low resolution understanding of this particular piece, but for whatever reason, when something is moving away and light hits it and comes back to us, there's a red tinge off that piece of light that's bounced back off it. Conversely, I believe if something is moving towards you, say, it will have a blue tinge. And there's a comparison here to the Doppler effect. The Doppler effect is, you've probably noticed this as well, if you ever stood on the side of a road waiting for a lift to hurling or a bus or whatever it was, if it's quiet, you'll see a car coming and then you'll hear the hum of the car to go as it goes past you. But typically, you'll see the car will come towards you, and before the car passes by your face, you'll hear it for 10 seconds. So for 10 seconds, there'll be an increasingly louder as the hum of the engine and the tyres in the road create sounds that are travelling towards you. But that sound is like that car that's coming towards you, you're seeing that via light that's hit that car, bounced off it and hit you. Now, if we could perceive light better, that car would have a blue tinge. We can't, but if you could, it would have a blue tinge. And as it moved away from you, it would have a red tinge. Now, we can't detect that, or we don't have I don't know if it's a failing on our eyes or on our brains for processing the light that comes into it. One or the other, we don't see it, but we do hear it. So for the 10 seconds you hear the car approaching you, as it passes you, you might hear it for a minute. You've probably noticed that. So it's coming towards you. You're on a dead straight stretch of road. It's coming towards you. It goes, but that, it fading lasts a lot longer. And that effect is called the Doppler effect. And it's very similar, if not practically the exact same, to that red shift phenomenon. Again, I'm only shining light on my, pardon the pun, shining light on my own ignorance of this. I can't explain it any better. That's me maxed out, which, isn't ideal. Like if I was to try and explain that to a kid or even an adult or even to yourself listening, you know, you're none the wiser. You might kind of know what I'm talking about, but I don't have a high resolution understanding of that phenomenon. But anyway, the fact that when we noticed, or when I think it was Hubble noticed that everything furthest away had a red shift on it, he proved that everything was moving away from us, at least as fast, if not faster, than the speed of light. So he theorized then that if everything is moving away in all directions, then if you wind back time, then everything will be coming together all the way up until the point whereby everything will be encapsulated in the tiniest point of space and time. And that's basically the Big Bang. Now, when the Big Bang blew up, it didn't spit out galaxies and planets and stars. It spat out empty space. Because remember, you couldn't look at the universe big banging, for want of a better term, because you'd have to be outside of the Big Bang to look at it, and there is no outside of the Big Bang. The universe as we know it is encapsulated within the Big Bang. So when the Big Bang banged, and as I said at the outset, it probably didn't make any noise because, well, for a start, there was no one there to hear it, but sound needs a medium like air or water in which it travels. And I don't know if at the Big Bang there was such a medium, say. As far as I'm aware, there were subatomic particles like protons and neutrons and quarks and stuff like that. So not even atoms, smaller than atoms, that were created. They paired up somehow. Electrons come into the mix at some stage, I think, when the universe kind of cooled down, because at the start, I think it was infinitely hot. The universe was infinitely hot because there was so much matter in such a small space that, generally speaking, when you compress things, they tend to heat up. But anyway, so the universe exploded into something from nothing. Subatomic particles, which were created in the Big Bang, kind of joined forces and created stuff, the first of which was hydrogen. So if you're familiar with the periodic table of the elements from school, just Google it and stick it into Google Images. Periodic table of the elements. You'll get this graph that you'll have all seen at some stage. But up in the top left-hand corner of that graph, you're going to have hydrogen, then helium, then lithium and beryllium, and etc. And as you read the table from top to bottom and left to right, they get more complex. So hydrogen is the first one, the first element, and it's the most basic element. I think it might only have, again, my chemistry is terrible, maybe one proton and an electron, or maybe a proton and a neutron. I think maybe a proton and a neutron and an electron. I don't know. Again, just shining light in my own ignorance. That's something that I need to understand a lot better. So, yes, it created, once the universe kind of cooled down a small bit, all the subatomic particles kind of clumped together and created hydrogen, which is a gas. So now in the early days of the universe, you have gas. Clouds of gas. Enormous clouds of gas. Because remember, the universe is expanding faster than the speed of light, and light's fucking fast. I don't know how many billions of miles it is a second or whatever. I don't know how fast it is. But anyway, another thing is relevant here, and it's time. So a second after the Big Bang was all of time, because time was created in the Big Bang. But when we try to break down mathematically what happened directly after the Big Bang, say, we have to ask ourselves, well, not that we have to ask ourselves, but we need a smaller unit of measurement than a second. Now, you could say split seconds, which I think are hundredths of seconds. But even in the first 100th of a second after the Big Bang, that was all of time. So much happened in that first split second that we have to further subdivide it. But when I say further subdivided, I mean we need a new measurement of time, which is infinitesimally small. Like, so small you can't get your fucking head around it. And they call it, I think it's called a Planck time. I think it's Planck. There could be a K or a T in there somewhere. But I think it's called a Planck time. And to give you an idea of how small a unit of measurement a Planck time is, or it could be I don't know if it's a Planck time or a Planck second, something like that. But it's a unit of time. It's infinitesimally small. And just to put it into perspective for you, there are more Planck times in a second than there have been seconds since the Big Bang. And that's easy maths. So you take, what was it, let's say it's 14 billion years. You take 14 billion, multiply that by 365 days in a year, obviously. Multiply that by 24 hours in a day. Multiply that by 60 hours, 60, which is minutes in the hour. Multiply by that by 60, which is seconds. And whatever number you have, that's the amount of Planck times there are in a second, thereabouts. So a fucking phenomenally small piece of time to subdivide the stages of development since the Big Bang. So, universe explodes, all this space stuff cools, condenses, forms massive gas clouds. Now, here's an interesting thing about space and weightlessness. So, there being no gravity. There was no, well, as if I said there was no gravity. No, there would have been gravity, but there was nothing to stand on at this stage. It's just gas. And I don't even know if there was dust. Probably not. Just gas. Hydrogen, specifically. But here's an interesting one for you. If you get a little empty vial and you put a bit of dust into it and close the lid and bring it up into space, it'll look cloudy with the dust that's in it. Let's say if you put a bit of flour into a glass jar, bring it up into space, and the flour will just, it might look like smoke because it's just, you know, it's not sitting on the bottom, it's just floating wherever it floats. But if you leave it alone, it will actually clump together. And I think it's electromagnetism that does this, I'm not sure. But it clumps together, it's just something that happens. So, in the early days of the universe, shortly after the Big Bang, when everything cooled down and hydrogen gas was created, I think it clumped together via electromagnetism, or something to that effect. So, the clouds became kind of denser clouds. And as they became denser, gravity became a thing. Because the fact that there was so much mass, there was so much stuff, it actually started warping space-time, which is the kind of material of the universe. That's a terrible way of phrasing it, but I'm at a loss to understand a better way of putting it. Basically, the giant hydrogen clouds collapsed in on themselves, creating liquid balls, basically. And as these balls grew, they became bigger and bigger and bigger and bigger, and until they, got to planet sizes and bigger. So you've got these huge balls of hydrogen gas, liquid hydrogen actually at this stage. And the bigger things got, the more gravity they had, the more it swallowed, the bigger they got, the more it swallowed, the bigger they got, the more it swallowed. And you had this kind of runaway positive feedback loop thing happening. And then big balls of hydrogen would attract other balls of hydrogen. They would merge, and these balls just got bigger and bigger and bigger and bigger until the weight of themselves was so intense on themselves. These things are constantly, from the center of them, they're constantly pulling themselves in. Gravity is sucking everything in. It's not really sucking everything in. That's the wrong way to conceptualize it. But basically what happens is pressure builds up at the center of these balls of hydrogen. And when the pressure gets to such a point whereby the hydrogen atoms are pushed together so tightly, they fuse. And that's fusion as we know it, not fission. Fission is what we use in nuclear power plants, but fusion is what powers stars. So at the center of these balls of hydrogen, it became incredibly hot and incredibly dense, and a mixture of this heat and density created a fusion reaction. Once fusion took place, fucking kablamo! It exploded. And the hydrogen atoms were burst into subatomic particles. Those subatomic particles ripped through all the other hydrogen molecules and blew them apart, which blew more apart, which blew more apart, and then you have this perpetual nuclear explosion, which is essentially what a star is. Like our sun, that's a perpetual nuclear explosion. So, all of a sudden, photons were being spat out of these things that we now call stars, and there was light in the universe for the first time. I don't know the timeline. It could have been 1,000,000 years, it could have been 100 million years after the Big Bang, it could have been 1,000,000,000 years. It was, way back at the start. We've got stars, we've got light, we've got no one to fucking see anything, but there's light in the universe, and the universe is just populated with mostly stars and dust. But some of these stars even as they were perpetual nuclear explosions, continued to get bigger. Even though they're burning up their hydrogen all the time, they continued to get bigger because they were still hoovering up all the other gas that was out there, all the other hydrogen that was out there, and whatever space, debris or stuff that was out there. So a lot of them got bigger and bigger and bigger. A lot of stars would have swallowed other stars, getting bigger and bigger and bigger and bigger and bigger. And there's two ways that these stars ended up. Some of them just burned up all their fuel and basically extinguished. They went out almost like a candle that runs out of wax, just kind of goes out. But some of them get so big that when they use up all their... So there's immense pressure being pushed internally on these balls, on these stars. Massive pressure being pushed in. But the reason that they don't collapse in on themselves, under the weight of themselves, and rip a hole through space-time and create black holes, is because they're constantly being pushed out by the perpetual nuclear explosion. But when that fuel source runs out, and they're no longer perpetually exploding, the whole thing collapses in on itself. And it'll either go out, or it'll supernova. And what it means to supernova is it all collapses in on itself to the point whereby it just blows itself apart. Now, I could do a podcast on supernovas because they're fucking savage. And there's a bigger version of a supernova called a hypernova, which is even fucking more savage. But anyway, just to give you an idea, in your average in your average galaxy, there could be hundreds of billions of stars. If one of them was to explode and go supernova, it will outshine the other 100 billion stars in that galaxy. So think of the sun and then think of something that's 100 billion times brighter. And that's the kind of thing you're talking about with a supernova. Interesting thing about supernovas is under that immense process, new particles are formed. So at the start we just had hydrogen, then fucking boom, stars started supernovaing and hypernovaing, and it literally created new atoms, I suppose. So you're moving further along down so you've got hydrogen, the next one was helium, and then a helium star blew up and it created lithium, and then it joined with another one, and then you've got stars with hydrogen, helium and lithium, and they fucking supernovaed, and then you got beryllium, and then it just went on and on and on and on and on. Until now, which I think the universe is kind of stable enough. I don't think any new shit is being made. It might still be being discovered, but it's not being made. Another point, I'm just going to completely ignore dark energy and dark matter because I don't even have a low resolution understanding of that stuff. I can't get my head around what that is. I just know there's loads of it, and that's about the height of it. Anyway, you've got all these other different elements now. So what happens is the universe is being continually populated by all these explosions, and there's new dust and new clouds and new stuff. And carbon gets created along the way. Very important. Carbon will be useful later for something we call life. All life that we know of, at least, is carbon based. Which is kind of cool because it means that from the carbon and everything else that is in us to make us us, we are stardust. We are literally stardust. You couldn't make a human being or any life as we know it without hydrogen stars supernovaing, creating newer elements, creating new star systems, them two supernovaing, and it's just, we're stardust. It's fucking class. If you're interested in that kind of stuff, us being stardust, Google, what's his name? He wrote a savage speech that I'm due to actually cover. Carl Sagan, The Pale Blue Dot. I'm hoping to do a cover of The Pale Blue Dot. So Google the Pale Blue Dot. It's fucking class. But it might pique your interest in that guy who I just mentioned and have since forgotten. Anyway, so now we have a load of other dust things in space. Now that condenses, gets pulled together by electromagnetism, gravity kind of kicks in, it gets bigger and bigger, and now you have things that are spherical because all celestial objects tend to be spherical, because in space there's no kind of up or down or left or right. So everything of sufficient size, at least, gravity pulls it in to form a circle. An interesting thing about planets, you've probably heard of Pluto. You might have been brought up being told that Pluto was a planet. But then a couple of years later, Neil deGrasse Tyson and a couple of other astrophysicists went, hang on a second, if you're going to call Pluto a planet, you're going to have to fucking name the 1,000 planets that are in the solar system. Too small. One of the things that made it too small was that it wasn't spherical, because it wasn't of sufficient size to have gravity pull it down to make itself a sphere. Anyway, we've now got planets. So I don't know, the Earth I think formed about 4 billion years ago, thereabouts. Basically what happened with our own star, when it was a big ball of gas, it condensed, became a big ball of liquid, grew more, or got bigger and bigger and bigger, had a fusion explosion in the middle of it. Didn't blow up, but ignited, so it lit up, it came alive essentially. It became what we call now the sun. Shortly after that process happened, the sun would have been surrounded by a disk or a sphere of sorts of space stuff, almost like dust, bits left over from other stellar explosions and supernovas and hypernovas and such, and it started to condense amongst itself. Now, a lot of this stuff was kind of almost dusty and not flammable, essentially, and a lot of this stuff, and also a lot of it grew to a certain size, so it mightn't have been rock, it might have been gas, but it didn't grow sufficient size to actually ignite. So you're just left with a big ball of gas, basically, which is essentially what Jupiter and Saturn are. There's no land on either Jupiter or Saturn. If you jumped off a rocket that was hovering over either Saturn or Jupiter, you just fall straight through its atmosphere until the weight of the gas kind of crushed you to bits. There's no solid surface as such, unlike the other rocky planets. Anyway, Earth formed within this dust cloud or disk that had formed around, or that hadn't formed, it was kind of left over after our sun igniting and stabilizing. So we're orbiting around the sun. When all our dust kind of collected and congealed and was being pulled together under the force of gravity, it was also being bombarded by shit that was just basically flying through the universe. Because when supernovas explode, they blow the fuck up, like. So they would have sent all sorts and manners of stuff flying out in all directions across the universe. And that stuff, because there's no atmosphere in space, once that stuff, was propelled from a supernova, it just fucking kept going and going and going. There was no air resistance to slow it down. It just fucking went for the horizon. And after a while, the universe was full of shit just fucking flying around the place. Everywhere you looked, something was fucking smashing into something else. Because the things that were flying around were guided towards other objects via the warping of space-time and gravity. So Earth would have been continuously bombarded with asteroids. Now, when these asteroids hit the Earth, they would have had the energy of, thousands of hydrogen bombs. So that it's like multiple enormous nuclear explosions going off on the surface of Earth, all the time, all day, every day, for possibly millions of years. So what the Earth is now is basically a big ball of rocks that are both molten and on fire. And this was the norm for ages. And then it cooled. Over time, not as many things started. Over time, there wasn't as many kind of bits flying around the universe. After a while, things kind of settled down. So after the first 10 billion years, things had kind of settled in the universe. It wasn't the shooting gallery that it was for, let's say, the first 10 billion years. So Earth is orbiting the sun, minding its own business, and then, would you believe it, another fucking planet, I think it was called Titan, hit the Earth. Their orbits collided, or I don't know how, if it even was called Titan, but the other planet that was smaller than Earth, I don't know how it came, I don't know how its trajectory veered it towards our kind of flight path around the sun, but we collided anyway, and it basically obliterated the whole planet. Not that there was anything on it. It was just a big ball of rocks that were on fire. So what happened then was it pretty much smashed the Earth to bits, and over the next so many million years, it formed again, but it didn't. It absorbed, let's say, 2/3 of the planet that smashed into it and nearly obliterated it, and the rest that was left was kind of spinning around Earth in a disc, a sphere slash disc. Again, like what all the planets were made of when the star ignited. We were left with all this stuff outside of our planet, and it kind of collapsed on itself, and we ended up having this thing kind of almost following us around. And that's what we call the moon. That's basically what the moon is. It was a lot closer when it first formed. So the tides back in the day would have been a lot more pronounced than they are now. Speaking of tides, at this point there's no water on Earth. I don't think. Not yet. No, of course there's not, because it's a big ball of flaming lava. So there's no water. But comets, which are big, massive, like mountains of rock and ice, which orbit stars. So if something's just flying through space, it's called a meteor, I think. But if something's orbiting a sun, or a star, should I say, it's a comet. I might have those distinctions kind of wrong, but they're thereabouts. But we would have gotten hit by comets over the years as well. So all the water that we now have on Earth, all of it, every fucking drop of it, came from comets. There was nothing but melted rocks that were on fire. And then we got hit by comets, which, as the comet hit us, it would have vaporized all the water, because it would have hit us in the form of a fucking nuclear explosion. So all the water was just instantly vaporized. But it didn't disappear. It kind of hung around the Earth, almost like a big cloud, and then it fell as rain. And that kind of big cloud is what we call our atmosphere. It's fucking still there. So it fell as rain and essentially flooded the Earth and cooled down all the melted rocks. So now you've got a liquid ball of rocks with what we actually call a crust around it. And that's the Earth's crust. If you drill deep enough, and you're on Earth, if you drill down deep enough, you'll get to liquid rock, the liquid rock part of the Earth, which essentially just hasn't had time to cool down. It will. In another 10 billion years, planet Earth would probably be, I was going to say it would probably be solid rock, but it won't be, because of the amount of mass that the Earth has and the pressure that it's exerting inwardly on itself all the time. I think it's that pressure that actually maybe not melts the rock, but stops the rock from cooling. Now, the crust isn't like the skin on, it is almost like the skin on an apple. I think the skin on an apple analogy will give you an idea of how thin the crust on Earth is. I think they're vaguely comparable. That the crust of the Earth is in proportion to the skin on an apple. I think, stand to be corrected on that. And again, if I say anything that's either completely wrong, slightly wrong, or I'm missing something, imoffthelead@gmail.com will get me. I'd be grateful to hear from anybody on anything that I ever mention. So, we've got a bit of stability in Earth. We have land, and then we have rain, and then we have oceans, and then we have poles. So at the opposite ends of our axis. So the Earth is spinning, like most celestial objects, and it's also traveling around the Earth. But the axis that it spins on, as it travels around the sun, is what we call our north and our south poles. And because of the lack of light that they get from the sun at different times of the year, that means that the oceans that are there are frozen solid. So that's why it's full of fucking 40 below and snow at both poles. It's because of their orientations away from the sun. It's a good job, put it this way, it's a good job our Earth rotates. It's a good job that we have night and day, because if it didn't rotate, and that's what causes night and day, if it didn't rotate, one side of the world would be daytime and one side of the world would be nighttime. But one side of the world would be on fire and one side of the world would be fucking frozen in time. So it's a good job we have that kind of dichotomy between day and night. It's also a good job that we're in what's called the Goldilocks zone. Now the Goldilocks zone is a position, it's like a belt that surrounds a star. If you're closer to the sun and therefore out of this belt, all your water will be boiled off. If you're away from the sun and out of this belt, all your water will freeze solid. And as far as we know, the only thing that you need for life, at least carbon-based life that we know of, the only life that we know of, you need liquid water. We're fairly sure you don't need sunlight. We're fairly sure you don't need anything else, essentially. Just water. Maybe something else. We haven't kind of figured that out yet. But I'm going to get to that, because the life starting is almost equivalent to the Big Banging. Something happened, and then, you know, the rest is kind of history. So I think it was about 4 billion years ago everything kind of stabilized. So 10 billion years after the Big Bang banged. Like, I've glazed over that 10 billion year quite nicely. One thing I didn't mention is the formation of galaxies. So all over the universe, you had kind of all these gas clouds condensing, forming balls of liquid hydrogen, igniting, becoming stars, supernovae, and all that crack. And this is all kind of happening everywhere and nowhere at the same time, because the universe is infinitely expanding in all directions faster than the speed of light. But hundreds of billions of stars at a time kind of started rotating around each other, and over billions of years became relatively stable and created things like galaxies. And the galaxy that we live in is called the Milky Way, which is kind of cool. And you can actually see the Milky Way when you look up at night, if you have a dark enough sky. It used to be, it's there every night. We just can't see it because of light pollution and clouds, obviously, and ceilings. That's the worst. We spend all our time in fucking doors these days, even during the day, never mind at night. But anyway, different topic. Oh, speaking of looking up at night, this weekend, so today is Friday the 10th of August, I think. I'm fairly sure it's this Sunday night, so that'll be the 11th, is it the 12th? I think it's the night of the 12th, the morning of the 13th, is the height of what's called the Perseid meteor shower. Not to be missed, folks. If you can get yourself in a dark spot, and I don't mean under the stairs, if you can get yourself away from towns and cities and lights generally, get out into the darkness as best you can and look up. Put something on the ground, get a pillow or a sleeping bag or whatever, lie down, look up, give it at least half an hour. The reason I say you give it at least half an hour, provided that there's no fucking clouds now, ideally you want to see a full starry sky. But the reason I say give it at least half an hour is because A, it's going to take your eyes 20 minutes to fully adjust before you see anything, and B, you're going to want to give yourself 10 minutes of having good night vision to actually see anything. But it can be fucking class. The last 2 years, myself and the lads have been out, past guest and friend of the show, Dave Webster, and I can't remember who joined us in the other nights, but anyway, for the last 2 years, it's just been a cloud fest. It's been so torturous. The biggest event of the year from a stargazing perspective. You look up and all you can see is the bottom of cunting clouds. But I think it was 3 years ago we had clear skies. It was fucking spectacular. If you've ever thought you've seen a shooting star, if you've ever done a bit of stargazing, and you might kind of go, oh, was that one? Oh, did I see that, or did I make that up in my head? Because especially if you're lying there for an hour or two, you kind of start seeing what you want to see. But the thing about the Perseids is, not only is the frequency of them, you're expecting, it could be 70 in an hour, or more maybe. They tend to be kind of brighter than usual, fireballs. So it's fucking gas. I remember, I think it was 3 years ago, there was a gang of us here at the house out in Kilberry, under the looking up. And you'd be lying there in silence for the most part. You'd be chatting away, like. But then you might go, oh, did anyone see that? And someone might go, oh yeah, I saw that. And I was like, oh yeah. Once you thought you saw it and someone else thought you saw it, you can be fairly sure that you both did actually see it. And then you go, oh, what was that? Was that something? Anyone? No one saw that one. Okay, that was maybe just me, or maybe I did see one, but you know, it wasn't that impressive. And the next minute, everyone at the same time doesn't say, did you see that? We all burst out with, whoa! Because it'll be that fucking impressive. Fucking shooting stars are fucking class, lads. If you've never done stargazing and you're free this Sunday night, like, camp out if you can, but at a minimum, you know, fucking free yourself up for an hour, you know, Sunday night, or even tonight or tomorrow night, because what I'm talking about, this meteor shower, it peaks Sunday night and Monday morning. So after dark on Sunday night, that's when it peaks. But it's happening above us now. As I record this, those shooting stars are happening. You just can't fucking see them because it's daylight. But they've been happening, like, meteor showers typically last about a month, I think. So they would have started, let's say, 2 weeks ago, peaks tonight, and then trails out for 2 weeks. But the peak of it is where it's at. It's where you're going to see all the big ones. But anyway, interestingly enough, meteor showers are when, as comets orbit stars, especially when they get closer to the star, the heat of the sun vaporizes the comet itself. Now, not the entire thing, just the kind of surface of it. And these things are the size of fucking mountains, basically, big mountains at that. So losing a bit of their stuff isn't, it's nothing. But they kind of leave this cosmic snail trail behind them. And what happens is when Earth is traveling around the sun, orbiting around the sun, it's traveling at, I don't know what it's traveling at. It could be 100,000 miles an hour. I'm not actually sure. But what a meteor shower is Earth, as it orbits the sun, it passes through one of these snail trails. So when you look up and you see something streaking across the night sky, that's a shooting star. That's generally a piece of something, a piece of rock the size of a grain of sand to a pea. Like, something the size of a pea will light up the fucking sky. Something the size of like a big rock will look like we're being invaded. Like, it'll look like a fucking missile streaking across the sky. And then bigger things, like anything the size of a car, typically will actually explode in our atmosphere. And when I say explode, I mean blow the fuck up and make it look, for a couple of seconds, make the night look like daylight. But anyway, they're relatively rare. But these little grains of like dust or pea-sized pieces of rock that light up the sky, they're traveling at astronomical speeds, and that's what causes them to basically glow and explode. But interestingly enough, they could be just, we often, from our perspective on the surface of Earth, it looks like they're flying across our sky. But I think what's more accurate is that they're just sitting there in space, not doing anything. And we actually hit them at whatever speed Earth travels at. That's something that I should know, the speed Earth travels around the sun. But anyway, so what did I glaze over? We were a big ball of flaming rocks, then everything cooled, then we had water, and then we had ice caps. And yeah, so then the plates. So the skin of the apple analogy is good to give you an idea of how thin the Earth's crust is. But it's a bad analogy because it might leave you with the impression that the Earth's crust was like the skin of an apple and didn't do anything. It just kind of sat there. But it didn't. Imagine this. Imagine you get a knife to the skin of an apple and you start kind of carving it up, and you carve it up into 5 or 6 independent pieces. I can't remember how many plates that the Earth's crust is made of, but it's made of independent pieces, basically, like a jigsaw puzzle. And they interact with each other. Some of them are pulled apart, and when plate tectonic plates, so big chunks of the Earth's crust, are pulled apart, something has to, it's not just going to create a space of emptiness. Lava, molten rock from the deeper parts of the Earth actually oozes up. So when the plate tectonic plates move apart from each other, lava gets oozed up and essentially new land is created. Now conversely, sometimes the plates move together and they push against each other and they buckle and push kind of upwards. And that's what mountains are. So it's dynamic, it's fluid, it's always changing. Back when the Earth first kind of formed and settled between 3 and 4 billion years ago, there was only one ocean and one mass of land. That one mass of land was called Pangaea, I think. But over time, it kind of shifted and moved around. And you probably know from like primary school or secondary school geography that when you look at a map, look at Africa and look at South America. And if you can imagine pushing the two of them together, they kind of fit. And that's because there's a line going through the Atlantic. I think it's called the Mid-Atlantic Ridge. And that's where the two plates that Africa and South America meet. But they're pulling apart. So they're literally moving away from each other. So if you reverse back time, Africa and South America would interlock, to give you an idea of how plate tectonics kind of move around. Anyway, somewhere deep underwater, you had what were called geothermal vents. So if you can imagine, like the oceans, it could be a couple of miles deep. And at the bottom of that, you have the crust, which is underwater. And underneath that crust, you have, almost like an ocean of lava, molten rock. And it kind of pierces through, almost kind of like a mini volcano under the sea. Kind of, not quite. Those do happen. And what happens then is the underwater volcano erupts, but instead of creating a mountain or a mountain slash volcano, what we would see on land, it tends to create islands. They erupt and cool down and erupt and cool down and erupt and cool down, and they stick up out of the sea's surface. They protrude the surface of the sea, and you have islands. So that's how islands typically get created, through volcanic activity, which is interesting because if you've ever heard of the Galapagos Islands, they kind of sprung up out of nowhere at a certain time. So the world was full of life, and then these volcanoes erupted under the earth, under the oceans, created new land, and then life from thousands of miles away ended up on these islands. Whether it floated in the sea, or it fell from the sky, or was carried off in a fucking tornado, or whatever it was. And it was isolated, and it actually started its own evolutionary path. So that's why places like the Galapagos were so instrumental for Charles Darwin to understand how evolution actually took place. He saw this really isolated place and copped basically what was going on. But I'm getting ahead of myself a little. There's geothermal vents under the oceans. And at these geothermal vents, there's an awful lot of kind of chemical shit going on, because there's, between the heat of the molten rock and the water and its interaction, it creates almost like a chemical soup. And it's theorized that this is where the first life formed. And like the Big Bang, we think that's what happened, but we haven't quite nailed it yet. So we're thinking now that that's where life started. Single cell life, as basic as it can get. But it had, strangely enough, how the fuck it did, I don't know, but it had DNA. It had instructions on how to make itself, and more importantly, make copies of itself. Because once it was able to subdivide and make copies of itself, and regenerate itself by, feeding on whatever it was feeding on, whether it was, it obviously wasn't life because it was the first life. So, the first life can't feed another life because, it's the first life. So presumably it was eating some sort of chemical soup. I don't know. I have a very low resolution interpretation of exactly how this process happened, like I do the Big Bang. But anyway, so single cell life became a thing, and then it started to evolve as best we know it. So it started to subdivide for a start. So it started to make copies of itself. So it started making more and more and more and more of itself. And once it was more and more and more and more of itself, it gave itself, unconsciously obviously, because nobody's guiding this. I'm not making a case for it. This is where God jumped in and created Adam and Eve, or Adam and Steve, depending on what way you're inclined. But anyway, so single cell life just basically started somehow. I don't think we really know. And it started subdividing and making copies of itself. And it proliferated, is that the right word? It exploded basically. It caught on, so now the oceans are full of this life. And over time, it changed through a process called evolution. So one of the handy little things that happened was, for example, let's say there was more chemicals where it was darkest, so at the bottom of the ocean, hypothetically. It became an advantage then if even a single cell or a slightly more multi-celled organism could distinguish light from dark, because anything that could tell that it was bright, say, knew that it was in the wrong place for the abundance of food, which is lower, for argument's sake. So it gave it an advantage. So if you were sensitive to light, it meant that you could get the fuck away from it. If you were getting the fuck away from light, it meant that you were heading towards darkness, where, let's say, potentially there's more food. So that became an evolutionary advantage. So that's what survived over time. Okay, so that's the start of the evolution of the eye, by the way, just by being able to distinguish night and day. Then again, I'm glazing over a lot of this massively, but essentially what happened was some of this very basic life developed an ability or a capacity to eat other life, and all of a sudden you've got predator and prey, and you've got an arms race. Because if you could make out light from dark, that would mean that you could see dark in light. So if you're surrounded by light and there's a speck of dark, you can identify that as something. And depending on your orientation, whether you're a predator or a prey, that something is something that you want to eat, or that something is something that wants to eat you. So you're either inclined to go after that shadow in the light, or get the fuck away from that shadow in the light. And again, this arms race just explodes. So you're left with kind of predator and prey. So moving becomes a thing. You had to move, let's say, away from light towards darkness, or vice versa, especially if you started to photosynthesize. So at some point in time, life discovered that it could harness the energy of the sun, essentially, and grow. So think of something like an algae or something that you'd see in the ocean, a kind of plant-ish based substance which processes light into sugar, creating energy, blah blah blah. So you've got an incentive to find light and stay in light and keep away from darkness, and you have an energy source. So what the fuck happens next? Oh yeah, the ability to move towards or away from that light is obviously key. So the things that are chasing you, the faster they are, the more successful they are. You that's been chased by something else, the faster you are, the more successful you are. And this arms race just, as I said, kind of explodes. So eyesight gets better. They can better define the shapes. So some of them can distinguish, what's the same as them and what's different. Maybe that's the fucking origins of racism right there. Who knows? And the things that can move faster either get to their prey quicker or get away from the prey quicker. Obviously an evolutionary advantage. So the better you were adapted, the more successful you were at reproduction, and the more successful your offspring had of surviving and proliferating, again, if that's the right word, and going forth and populating the world. So I'm going to jump to a couple of different stages. So I kind of half touched on how the eye and how movement became a thing. Somewhere along the way, these little organisms developed a stiffness to them, which made them more effective at moving through the water. Because if you can imagine being made of jelly and trying to swim, you'd be flopping around. Like if you'd no bones and you tried to swim, you just sink. You might be able to move, but you're not going to be able to stretch and pull back water and stretch and pull back water. But if there was rigidity to your jelly-like state, you would have an advantage. So essentially a stiff rod started developing in certain types of primitive life, which is essentially a spine, which was the precursor for all animals with skeletons. So if you had a spine, you were a something. There's a classification that covers things with spines. Thereabouts at the same time, one type of animal or life was creating a stiffness inside them. I think prior to this, some of them had created a shell, which makes sense. You want to protect yourself. You want to, get tough skinned, as the saying goes these days. But that was literally true when life was starting out. The tougher your skin, the harder it was for your predators to eat you for a fucking start. So out of this tough skin came a jaw as well. So that was another classification. So there was, by the way, the rod that was inside things to make it more rigid so it'd move either towards something or away from something, that's it's called a skeleton. But the shell, that's called an exoskeleton. So an exoskeleton, like insects have, they have a hard exterior and a soft interior, as opposed to mammals like ourselves. We have like a hard interior, our bone structure, with a soft exterior. So they're indo and exoskeletons. So what the fuck were the things with spines called? Can't believe that's failing me now. I think crustaceans were the things with the exoskeletons, with the hard shells, the hard exterior. Vertebrates, there we go. So you've got, and again, I might be mixing up the timeline here. Presumably you had, oh, actually, I must mention the Cambrian explosion. So the sea is a soup of primitive life. And that's what it is, forever, for a billion years or whatever it was. I can't remember. But at a certain period of time, I think it was thereabouts, let me think, maybe I think it was 400 million years ago, thereabouts, you had what's called the Cambrian explosion. So up until the Cambrian explosion, you're talking, algae and shit, and stuff that kind of floats and isn't really, it's not exactly a plant or an animal, it's just kind of life. But then the Cambrian explosion came along, and the Cambrian explosion it's a period of time called the Cambrian, a couple of 100 million years ago, where for whatever reason shit got real, and you started getting animals with these interior rods, what we would call spines now, vertebrates, that classification of life. And there was also an explosion in exoskeleton crustaceans. So think of kind of woodlouse. Can't think of what they were actually called. Trilobites. There we go. Trilobites. There was an explosion of all this shit. It just seemed to kind of happen for whatever reason. Maybe the earth got warmer or cooler, or there was more oxygen or whatever. But something happened and life just fucking went nuts. So, but it's still all in the water. There's nothing on the land. There's no reason for the seafaring life to go on land yet, because there's nothing on land. There's no insects, there's no plants, there's no nothing. Plus, I don't think we had an ozone layer like we do now, so it was, I think, mortally fatal for any kind of life to end up exposed under sunlight until our ozone developed. When that happened, I'm not entirely sure. But anyway, so we have stuff moving around, stuff fighting each other. The tides, as I mentioned, were far greater than they are now, say, because the moon was a lot closer, so its impact on the water, on our oceans, was a lot greater back then. So we had massive tides, huge tides. Like these days, the tide comes up the beach about 100 feet, maybe half a mile or whatever. But this would have been hundreds of miles. So it would have dragged all this life kind of onto Earth, willingly or otherwise. It didn't really matter. It was happening. So after, so many millions of years, life started to breathe air, which broke its tie to a degree only from the sea. So it could come out of the ocean onto the land by breathing air. So that was a new thing. In the meantime, now we've developed jaws and teeth and digestive systems and all that jazz. But look, I fucking hell, I'm here all day already. I can't fucking go into any more of that. Not that I know a whole pile about it. Anyway, so yeah, we start having animals that can leave the water by breathing air, which is great. But they're still tied to the water because they lay their eggs in the water. Then there was this kind of cosmic shift whereby animals started laying eggs with hard shells. So that meant that an animal could leave the water and not have to come back to the water to lay its eggs, because we evolved to lay eggs in water. But then we evolved to lay eggs on land, which cut our ties with the water, which meant that we could start basically populating the land. At thereabouts the same time, plants and shit started growing on the land as well, and there was a proliferation of insects, etc. So we've cut our ties with the ocean, we've got shit living on land now. There's a problem with the egg though, because you have to mind your egg or other animals will eat it. So there was a further development. We didn't lay an egg, we kept the egg inside us. And our offspring grew inside us. And we gave birth to it live. So that was another kind of cosmic shift in how life was able to survive. Because of the oxygen levels as well that the plants generated, the more oxygen that was in the air, it meant, I think, that things grew bigger, way bigger. Enter the dinosaurs big. Interestingly enough, I was only reading a book there last week. I gave it to my son Keown, who's just turned 4. And it's a dinosaur book that my parents gave me when I was not that much older. But there's a cool page on it whereby they're talking, it's a book about dinosaurs. There's a cool page where it says that it's theorized by certain scientists that the extinction of the dinosaurs was caused by an extinction level explosion caused by a meteor that smashed into the earth. But unfortunately, no such crater exists. So this is it's just a theory, no more. Now, we found that crater since. I think it's in a place called, its location is known as Chicxulub. So Chixulub, something to that effect. If you Google that, it'll come up. But basically, it's just off the north coast of Brazil. And there's a kind of, what's that semicircle shape called? A protractor type shape. Semicircle, maybe. There's a semicircle on land, and then there's the other semicircle on under the ocean, basically. And it was through potholing, which is the practice of exploring caves and shit, and lakes and lagoons and different things underground, that we actually discovered where this meteor impacted us. And the timeline, it was 65 million years ago. That's when the dinosaurs basically all died. So it was just kind of cool reading back on that. In my lifetime, we've discovered that Chicxulub crater, and like when I was growing up, we didn't know what happened to dinosaurs basically. And I'm not an old man, so it's just class. But anyway, so you had the ability to cut your ties with the water, which meant that you could populate the land. Then we started laying live young. Another thing that mammals did, as well as laying live young. Laying live young, that sounds weird. You wouldn't, I'd never say that my missus herself, like, I'd never say that we'd say gave birth. You'd never say she laid a child. You know, you lay eggs, you give birth to children. But I don't know, it's a weird distinction. Why don't we just say she laid a child? It's a weird one. Anyway. Another cool thing that mammals could do is we could regulate our own body temperature. And another word for being able to regulate your own body temperature is warm-bloodedness. We're mammals. So we give birth to live young, or we lay live young. We can carry around a food source for our young in the shape of milk produced by our mammary glands. That's also unique to mammals. And we can, very importantly, we can regulate our own temperature. So animals that can't regulate their own temperature are colloquially known as cold-blooded. So think of reptiles. A crocodile, when it wakes up in the morning, has to basically sit in the sun all day before it can heat itself up and do anything. Mammals can literally generate their own heat. Now, I heard a cool comparison here before. Between a lion, say, and a crocodile, both apex predators in their own classifications of mammals and reptiles. It takes 10 times more food to fuel a lion than it does a crocodile. So a lion basically needs to eat, once a week or every other day. A crocodile might, swallow a deer and not eat for fucking 2 or 3 years. And the reason for that is because they use up so little energy. Now, they're also very inactive for the most part, unless it's very hot. But anyway, we created live young. Then a certain proportion of the mammals that were kicking around at the same time as the dinosaurs, something like a fucking shrew or something, grew a little bit bigger, started swinging from trees. There was primates, then there was apes, then there was bipedal. Well, all apes are bipedal, all monkeys I think are bipedal. Bipedal being that we just stand up on our back legs. But that gave us an advantage of being able to look across grass fields and watch out for predators and hunt down prey. We also had opposable thumbs, which is a big evolutionary advantage. It meant that we can grab stuff and whack people with it, or animals, or dig up roots, or do different things. Our hand-eye coordination was good. Our brains started generating. So the first life that evolved wouldn't have had a brain, wouldn't have had a nervous system. It would have just been nothing, basically. But over time, while we were evolving outer shells and internal rods called spines and jaws so that we could bite and chew, and eyes, and we needed something to process all this stuff. So what made your jaw close when you were right in front of an animal? What made the light that hit you? What put that into something that you could make use of? Was a primitive brain. But there was some sort of an explosion with proto-humans, with what came before humans. So I think it was Australopithecus was the first proper human-like ape with a big brain that made tools and all this jazz. He was kicking it about, I think maybe even the best part of 1 million years ago. And then there was, I can't remember what the other guys were. There was Neanderthal man was in there, and the Cro-Magnon man, and there was a few others. But we basically evolved, like humans, me and you now, evolved from like an early human. That early human evolved from, you know, an early ape. That ape evolved from an early primate. That primate evolved from some sort of early mammal. That mammal evolved from, you know, you keep going back and back and back and back and back until you find what's called Luca, Luca, our last universal common ancestor. I'm not exactly sure what Luca is or if we've even kind of nailed down what it was, but essentially all life is life. So we're related to everything. Now we're closer related to some things more than others. And there's a weird distinction here because you might think that, let's say, humans are closer to crocodiles than we are whales. Okay, because if you lie down on your belly and bring your kind of knees up forward and bring your elbows in and kind of hunch down and almost crawl, if you were a little bit longer and you had a longer mouth, you know, you could see how you might have been a crocodile a couple of 100 million years ago. But a whale, you know, it's the size of a fucking country and it lives in the water and it can't even walk on land. And, you know, you'd think that they were completely different. Not the case. We're far closer to whales than we are crocodiles. We're warm-blooded for a start. We don't lay eggs. We give birth to live young. We have mammary glands, or at least the female of the species has mammary glands. We feed with milk, you know, etc., etc. So it can be very strange and confusing for everyone, I suppose, to realise that not only are we all linked, but we're not necessarily linked in the way you might think. Holy shit. Right. Yeah, so we're advanced animals. We've got stone tools and we can maybe think and work together a little bit. And then we start living in bigger and bigger groups. And as the groups get bigger, we start having kind of new problems, like, you know, waste. Like, you know, when it was just the three of us, we just shat wherever we want. But now there's fucking 10,000 of us and there's fucking shit everywhere. Not good. So, you know, we all started shitting in the one pile, but then we all got hungry because there wasn't enough, you know, foraging and hunting and gathering to feed so many of us. So the big eureka moment for humans was agriculture, which happened, I don't know, look, 50,000 years ago, maybe less. So civilizations basically started, but the first humans, the actual humans, not a proto-human, an actual human being, Homo sapien, us. We started out in East Africa. That's just how we happened to start out. Just like polar bears started out in the North Pole and penguins started out at the South Pole, humans started out in East Africa, somewhere, I think, Ethiopia, thereabouts. And as the climate changed, I believe we started in jungles because we were apes, we were living in the trees, remember? But as the climate changed, the jungle slowly disappeared. Now again, this happened over tens of thousands of years. The trees basically got shorter and shorter and shorter until it was grassland. And over that course of millions of years, we adapted to it. Now, most things don't adapt. The overwhelming majority of things just kind of die out because what they evolved to thrive in has now changed or gone, and they're not adapted to this, so they're gone. So pretty much, like, I think it's 99.999% of all life that ever lived is extinct now. So stuff kind of pops up and dies off all the time. The advantage that we had, I suppose, was that we were very adaptable. We could, you know, move somewhere colder, or it could get colder, and we had the intelligence to cover ourselves in the hide of the animals that we had killed to keep us warm, clothing. That was a big evolutionary advantage. Once we invented agriculture as well, it meant that we could stay in the same place. It meant that our time wasn't taken up by following herds of, you know, buffalo or antelope or whatever it was that we were feeding off, or maybe following different parts of different forests with fruit at different stages of the year. So that would have kind of kept us moving as well. But once we bedded down and had like fields of plants that we could eat, we started building houses, and not just huts that we could just pick up and move in the middle of the night. Permanent structures. And these structures, you know, you build yourself a nice house, then you build your kids nice houses, and then your friends come over, and then you get chatting to someone at a fucking lake and you say, here man, we've got it made over that hill over there, there's more food that we can eat, we've killed all the dangerous predators, there's a load of, you know, buffalo that kind of pass through every so often, there's no poisonous snakes, there's no fucking insects that'll kill you. it's pretty cool. So they attract more and more people. The more and more people that are there to talk about it, the more and more people they attract. And all of a sudden, you've got this surplus of food. You've got people with, time on their hands. So they start, making better spears or better, nets or bows or, vessels to carry water in so they can travel further and blah, 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 blah. And all this shit just kind of explodes. You've basically got a society then. And this happened independently all over the globe. It started in, I think, Mesopotamia, which is kind of northern, eastern Africa, thereabouts, between, I think it was two rivers, Mesa and Patania. I think there were two actual civilizations. The earliest that we know of, I don't know. Again, you're talking thereabouts, I don't know, 10,000 years ago. So, no time ago. Fucking 5 minutes ago. And it was happening in China. It was happening in North and South America as well. Interesting thing about North and South America, there's this area of the planet called, I think it was called the Bering Strait. And it was when you could walk from Asia to Alaska. So basically, I think either presumably the sea level, what's the opposite of rose? Sank, declined, went down. And it exposed the bottom of the sea, which you could now walk across. So people travelled from from East Africa, Ethiopia, thereabouts, up through to what we would now call the Middle East, where Mesa and Patania became Mesopotamia. And then we moved further out into Europe, and then we moved across Asia and up into Russia. These are obviously all modern terms, but we moved across the Bering Strait from Asia into North America, and then we travelled south down into South America. I don't know how the fucking Aborigines got to Australia, but they got there. Island hopping, probably. But anyway, so we've basically filled the world full of humans. Now, when I say fill the world full of humans, there might have been 1 million of us on the planet. And that million went to 2 and 3 and 4 and 5. And then I think it was somewhere in the last maybe 200 years that we went from 10 million to like, what the fuck is it, 7 billion or something? So there's just this big, huge, astronomical fucking explosion of us now. And we're, by all accounts, wreaking havoc on the planet. All very much by accident to a large degree. No one kind of set the wheels in motion to destroy the planet that we're on. But it makes a certain amount of sense that when life came about the way it came about, that we would just do our thing, kill all the animals and eat them. Like, we did that for millennia, with no ill effect, because we weren't making a big enough dent on the populations that were there. But then you had the Industrial Revolution, and you had shit like sniper rifles. Now it didn't take 40 of you to bring down a buffalo with fucking spears. One man could take out the entire herd in 5 minutes, provided he had enough fucking bullets. The same with the sea. Like, we've been hoovering fish out of the sea since we were able to throw a spear or cast a net, but we didn't really do it with the efficiency that we have now. I mean, Jesus Christ, you've got a ship the size of a fucking continent dragging a big net behind it throughout the ocean, sucks it in the back doors and spits it out the front door in a bird's eye box, frozen. Like, the scale of this is just astra-fucking-nomical. And the damage that we're doing to the planet is just literally catastrophic. But in a kind of a weird way, it makes sense that we would ruin our first planet, and hopefully we don't have to fucking flee this planet and move somewhere else. Hopefully that we can kind of get a handle on what climate change is, what's caused it, the best way to reverse it, because it's nice on Earth. But we don't need to save the planet. We need to save ourselves. The planet will be fine. The planet will be fucking grand, okay? You could get every nuclear bomb that was ever designed, let alone made, and blow them all up at the same time, and you could literally blow the Earth apart like a black cat banger. You could explode it. You could put a load of bombs in the center of the world if you could, and blow it to pieces and scatter it across the solar system. And, give it a couple of tens of millions of years, or maybe 1 billion years or so, and it'll make a new planet, and life will either form again from new, or it'll be populated from someone else. That's actually another interesting thing. One of the other hypotheses of how life actually got created was that it came from somewhere else, from another planet. that it evolved somewhere else and that it landed here on a, you know, either a comet or a meteor or just dust that got blasted off another planet. So yeah, that brings us from the Big Bang to now and the Industrial Revolution and the most recent revolution, which is the internet. And we haven't caught up with what the internet is and the implications of it. I personally believe that it's probably as big a seismic shift in our species story as not only the Gutenberg Revolution, which was the invention of the printing press, being able to write shit down and kind of pass it on through the generations. Bigger than that, as big as that, if not bigger, but as big and if not bigger than the Industrial Revolution. It's the internet is the next big thing, and we haven't really copped onto it yet. But we're beginning to, like the likes of me. Like I'm 34, and like 50 years ago, this recording that I've just made, if you could teleport the recording that I've just made 50 years ago, that would make me the smartest man that ever lived, bar none, I would imagine. Maybe not 50, maybe 100. No time ago. The smartest man imaginable. In just what I've said. Not everything else that's in my fucking head. Not everything else that I've mentioned on the previous episodes. The smartest man that ever lived. By a million miles. Now, not necessarily the wisest man that ever lived. And there's an important distinction. A friend of mine, future guest and friend of the show, Porrick Riley, actually put it quite succinctly. He said that these days our minds are overfed and undernourished. And I really, really, really like the way he phrased that. That our minds are overfed and undernourished. So we have all this stuff. We know all this stuff. I could tell you everything you could ever want to know about commercially growing pea shoots and selling them into the Irish market, or microgreens, or anything else for that matter. My level of knowledge of that is just off the fucking charts. And the utility in that is that it's my family's livelihood, which is fucking fantastic. But it doesn't really make me all that wise. It doesn't tell me, you know, how I should treat people who are very different than me. It doesn't tell me how I should govern, or not but how we should govern our society. So there have been far more societies in ancient history that were, let's say, more peaceful than us. Were they wiser? Were they more intelligent? Were they smarter? They mightn't have known as much stuff as we did, but they weren't stupid. I used to have this idea that people that lived, you know, hundreds if not thousands of years ago were stupid. Were they? Fuck. Like, the pyramids weren't built by anybody stupid. We didn't invent, like, stupid people didn't invent farming. But to try and bring this fucking, whatever this is, rant or whatever else, to some sort of a close, is that's my, what I would consider a relatively high resolution understanding of how I came to be sitting here to you today. Now, it's by no means extensive, and I'd love to get somebody in to actually have a conversation about this stuff so that we can kind of work off each other. But if you don't have that kind of a grounding, I think you're at a massive disadvantage when arguing with somebody who does. Because the more you can understand about what you are, the better you can try and figure out who you should be, who you want to be, and how best to make your way through this world that we've inherited. So on that rather philosophical note, I'll chat to you soon.